Indiana University East, School of Natural Sciences and Mathematics, Gibbs Energy and Chemical Equilibrium. So let's think about what happens and why. What happens if you say have a pure mixture? Okay, there's no chemical reaction. And so what if I keep mixing stuff? When would I minimize the Gibbs free energy? There is no enthalpy associated with mixing. However, there is as you mix it, you're going to increase the disorder, right? Because you've got different types of molecules there instead of a pure substance. So therefore, you will see that there is a minimization of the Gibbs free energy when you have an equimolar mixture of two different substances. So if the Gibbs free energy is the same in a reaction for the reactants and the products, then we would expect that the equilibrium basically at the midpoint, right? However, the reactants and products have different standard Gibbs free energies for the pure substances. So therefore, there are two things you have to look at. So here we have a reaction where the Gibbs free energy of reaction is negative. And therefore, if you think about the pure product and pure reactant, there's a difference. And so, and delta G really is the slope of this. And so here the reaction favors the product, but it doesn't go completely that way. Nothing does in reality. At equilibrium, the Gibbs free energy is minimized. So the slope of the Gibbs free energy against the extent of the reaction is going to be 0. And this is where the extent of the reaction we can get equilibrium. Okay, this is not really quite the mole fraction. I'm a bit loose and fast on here. But this is where if you have A going to B. Okay. But we can generalize by saying that at this point, we can find a point where delta G, the slope, at the minimum of this curve. And therefore, we can use this information to find out how the equilibrium constant, again, we're going to use the same definition as for reaction quotients. So Q is equal to K, where remember gases would be partial pressures. And solutes will be molarity. Then we know that delta G is equal to delta G, standard delta G, plus RT ln Q. So substituting in what we have here, 0 is equal to delta G naught plus RT ln of K. And so rearranging this, the standard Gibbs free energy is equal to minus RT ln K. And this is very important because you can then relate the standard Gibbs free energy, which is a thermodynamic quantity, to the observed equilibrium constant.